Okay, yeah. So we'll just be doing example problems for the exam. The exam will be on Tuesday, right? There's going to be, so I just made some notes. I haven't written the exam yet. But the topics in general that I'm going to cover, I'm going to read off, just so there's no real surprises on this one. I'm going to be doing timing diagrams. There's going to be probably 2 timing diagram questions. One of them will be for strictly combinational logic, which is similar to the one we did before, but for this exam, there's going to be delays in the gates. So I'll do an example of that. And the other timing diagram will be synchronous logic, something clocked. And we'll do an example of that in a bit. There's going to be some sort of design problem, design question. I think this one's going to have generics and or generate statements, almost certainly a generate statement in it. So like how we designed the adder, right, using a generate statement, that's the kind of thing that we'll do, is make sure you know how to use generate loops and are familiar with generics. Generics is particularly easy to look up, right? They're not difficult. Generates are a little bit trickier. Then there's going to be questions on counters, which I'll do an example today. Question on, probably more than one question on latches and flip-flops, right? And those are linked to counters as well as shift registers, which will be a question on shift registers. There's going to be something about muxes in there. And then some question about synchronous versus asynchronous, whether that's about counter, right? And there's going to be, I think, between 4 and 8, just short answer or multiple choice or true false questions, just something conceptual. And then, so in there might be where these synchronous questions are, like, what are the, which is faster, a synchronous or asynchronous counter? Or I might give you code and say, is this a synchronous or asynchronous reset, right? Just the idea of being synchronous or not. And that's more or less all. I think there's going to be 6 or 7 questions in addition to those 4 to 8. We'll see. Oh, and then there's going to be one question on addressable memory, which we talked about right after the first exam. So it's been a while. So I'll show you what I'm expecting on that one. It's not going to be too hard. It's just actually a requirement of the class. I have to test on addressable memory. It's one of the things you have to know. But right, it's really just what we looking at values in a table using muxes. It's really a mux question. But I'll point that out, kind of what I'm looking, what you need to know really coming up. So I'll start off with the timing diagram question. So this is really just an adder, right? A full adder that I've tied the 2 outputs together through an AND gate. There's nothing fancy on this circuit. And one of the things we always want to do, and I will try and provide it because otherwise it gets confusing, is label the nodes, right? Because if I call this D, E, F, G, and H, so take H, and I'll just call the output Z. Take H, for example. H could be really hard if you're trying to treat H as the complex of expression of it's right A XOR B and C or and, right? But it's not really a complex expression because once you have F and G correct, you're done, right? It's just an OR gate on F and G. So what I'm going to say is that the delay for all gates is going to be 10 nanoseconds. And then I will try and provide you guys with the diagram. If I forget, that's a big mistake because this is kind of hard and annoying to draw, and not what I want to test is if you can draw vertical dashed lines. So I could ask either to test some subset of inputs, or I may say exhaustively test this, right? If I'm just saying exhaustively test, that means I want all possible inputs of A, B, and C. I may end up providing the stimulus waveform for you because last time I learned my lesson, because what ended up happening is you guys, some people did the LSB first and some people did MSB first, and that made the grading difficult. So I may provide A, B, and C. If I don't, right, the way that you do this, if I say exhaustively test, is the same way that we would just count in binary, right? Where the first one is going to go 0, 1, 0, 1, 0, 1. The second one is 0, 0, 1, 1, 0, and so on. In this case, I'm going to say that the space between each of these is 10 nanoseconds. And I don't want to deal with too crazy of propagation delay problems, right? Because the propagation delay limits our ability to, well, it limits the speed of the circuit. If we go too fast relative to this time delay, we're going to have issues. So I'm going to use 10-second windows, but I'm going to do 20 nanosecond bit changes. So I'm going to be 0 for 2 on the first one. Six, 7, row. Okay. No delays on those, right? It's just A, B, and C. That's the input. I might provide you with that kind of waveform. And then it would be your job to come in and say, let's finish this timing diagram. And I would either provide all of the letters or say, give me all of the nodes and name them. And so let's start with D. Now, D is going to have one gate delay. That means we're going to have a 10 nanosecond delay from when the inputs change to when the output changes. So let's assume that D has been there, A, B, and C have been at 0, 0, 0 for a long time, so I don't have to worry about any propagation there. So XOR gate, right, is true if the two inputs are not the same, right? So 0, 0, 0 on A and B means they do start the same and are the same until this point, right? At which point they become different. But there is a delay of 10 nanoseconds before D can rise. Okay, and then they stay different. Even though it changes, they stay different, so I don't have to worry about that. Then they go back the same at this point, but it doesn't drop until a 10 nanosecond delay. So I'm just offsetting it by one set of bars. Let's keep going. They're back. So they're the same. They're the same. The next time they become different is here. All right, so all I'm doing is seeing where the input's going to change, drawing it to that line, and then delaying by 10 nanoseconds. So they're, and this is actually kind of interesting, because at this point, they're the same, they're different. So it rises, they're different, still different until that one, they're the same, and then it drops. Okay, so that's like the easiest case. There's one gate delay that I have to worry about from there, and the A and B's have the same gate delay. Okay, now we can do E next. E or F makes sense. So we've made D. G is pretty easy because it's, again, A and B. So maybe we'll do G next, but I'll just move on alphabetically for E. So E, right, is going to be another XOR operation, but I only have to worry about if D and C different. I don't have to worry about A and B anymore because I've done D. Again, if you tried to do A and B, if you tried to write this full expression for E, which is A XOR B XOR C, then trying to write out that would be really difficult. Trying to look at these three inputs and then do the gate delay in your head would be almost impossible. So make sure we just look at this. This is D XOR C. Okay, well, let's go ahead and say, when are they different? Well, this node, it changes. So with the 10 nanosecond delay, I jump up, stay high until they become the same. Go 10 nanoseconds after, and then drop. And now they've once again become different, right? So same, different. This different happens after a 10 nanosecond delay. And then different until here where they become the same. Same. And then different again, but that's off the map. Right? Okay. So you're starting to get this kind of delay, and it's kind of fun. In the other class, the last night, if you watched my video on this, I actually made a mistake. And I did this whole thing without the delay. And then I was like, oops, and then I did an overlay of the delay, and you can kind of see some behavioral differences between the two in that video. Because especially when you have like one that has no delay path and one that does, you can end up in situations where the width. So, and this is a perfect example of that. Notice how this is a 10 nanosecond space, even though my changes happen at 20 nanosecond intervals. Right, so this ends up being a smaller period of time. So it's possible with certain delay chains you can miss this number entirely in this test. Just something interesting. I'll try not to do something that convoluted to you guys. This is kind of like the worst case scenario that I would do. Okay, F is just D and C, right? That's easy. As long as we did D right, D and C is easy. So I'm just going to go until I find something. So C is obviously can't, D and C can't be true until that point, right? There's just no way for it to be because C is false. And then here is the first time that I have both C and D. So I'll go all the way to that point. It's going to go true with a 10 nanosecond delay. And then it's going to drop, but again, 10 nanosecond delay off the map. Okay. G. G is the one that I pointed out earlier, is super easy, right? Because G is just A and B. So can't be true until here. And so really it's this node at this point that I can be true. And then this node at that point. So we're false, 10 nanosecond delay true. And now we go back false because it's an and here with a 10 nanosecond delay. And then we're false all the way until that 10 nanosecond delay becomes true. H then Well, H is an OR operation of F or G. I only have to worry about these two. Just give the true with a 10 nanosecond delay. So there's a true here, shifted by 10 nanoseconds. And there's true here, shifted by 10 nanoseconds. The first block should be. Which one? Oh wait, no, there was. Sorry, there's a. Yeah, there's a line up here. Okay, H, E, Z then. Where does H and E? Well, here. And stops here. Right? H and E. True here, false there, and that's it. 10 nanosecond delay, rises, goes, false. And that's the right combinational timing diagrams. We did this one on the first, something like this on the first exam without the propagation delay. It kicked you guys' butts. It's kind of important, so I'm gonna put one up there again. This time it's just a little bit more complicated. I can also, right, throw in more complicated gates. I could be like X NORs, right, NAND gates. I haven't done that. I've stuck to kind of the simple ones. I could also, if I wanted, because I like test, right, I said I'm going to test about muxes, making sure that people are actually getting them. I could change the circuit and do something like, how would I want to do this? That. Right, there's a mux in that now. And it's not too difficult. It's just that you have to really think about what is happening and make sure that you set up the app before you do this node, right? Because you have to know what is F doing when the select chooses. Because if B here was 0, then it takes F. But if B is 1, it's taking A. Right, and it's just functioning as a pass through. And I might keep it right and say even this delay is 10 nanoseconds. Or I could be cruel and say something like, what is the structure of this mux? What is its delay, right? I could make this delay be different. And then you have to think back to what is a mux, right? How is a mux made? And that's easy, hopefully, to either derive or just remember because it's been brought up in the notes a couple of times. Make sure your notes are well organized. Again, this exam will be open notes, open book, open internet. You can take it from home. I would strongly encourage everyone to take it in person. The reason being that last year, my 2,700 students, the at-home people and in class people did about the same with like a 3% lower score for those that did it remote. This semester, exam 1, for both my 2,700 courses, the people that did it at home did terribly. Like really, really bad with one exception. So I don't know, we've kind of noticed in the department, I think you guys are all just kind of like burned out on the pandemic issue and being at home. I don't know if it's just family being home and around and distracting what it is, but be careful if you're taking it from home. It seems to have not done well for people. You still can, I'm not stopping you from doing it. Just be aware that it hasn't panned out very well for people this semester. Okay. I have one more timing problem that I could do, the combinational one, if we have time at the end. I'm not sure we will. So I'm going to move on to the flip-flop questions. So the question I could easily ask in the case of flip-flops is, well, I'll read it and then draw it because it makes a little bit more sense once I draw it. So a D flip-flop has its Q output connected to the J input of a JK flip-flop and its Q bar output to the K input. The input sequence of the D flip-flop is 1, 0, 0, 1. Draw the Q output of the JK flip-flop. Okay, so let me draw what I just said. So I said I have a D Q flip-flop with its Q output connected to J and its Q bar connected to K. The D flip-flop has an input sequence of 1, 0, 0, 1. So what that means is that the rising edges of the clocks I'm going to have so this is clock, my D input is going to be 1. So these are my nodes. One, and if you had to draw this yourself, if you're changing the inputs, I like to change the input on the opposite edge as what the trigger is, right? So this means rising edge. If I were to put a bubble there, that means a falling edge triggered device. You remember that, right? I don't do a lot with falling edge triggered, but I could. We had one homework that had some stuff on it. Okay, so I changed my data on the falling edge, and that's just typically good digital design practice. It is also very clear what the value is at the rising edge. So 1, 0, 0, 1. Right? 1, 0, 0, 1 are those rising edges. So that's what that input sequence means. Now, the way that I would, of course, recommend doing this is the way it's phrased, you could just try and skip straight to the Q, and that's how other students I've seen kind of do it. But I would recommend drawing in what are the J, at least the J, because K is just going to be not J, right? So we can easily do J and K without any effort once we get J. So what does a D flip-flop do? Well, on the rising edge, and it's going to go ahead and take this input, right? So to start out, I don't know. You can make an assumption, but I don't know what J is. After this rising edge of a clock, with a little bit of delay, right? And this is, again, what I encourage you guys to do is, even if I don't specify, make sure that you just give it a little bit of delay because it gets clear. The reason being, if I'm going from 1, well, let's say I have a clock here. And at the same time, I'm going from 1 to 0. There's kind of this question of, am I clocking in a 1 or a 0, right? And in real life, right, if you have real devices, we have the T setup requirement because it's unclear. But even in ideal devices, right, it's going to take the 1. Now, the reason for this is you can either consider it from the math approach where you're really taking the limit as we approach that point, which is 1, or you can picture it from the physics standpoint, which says, well, this change cannot be instantaneous, right? And so there's a slope to it, right? There's a slant as it tries to make that transition. So even if there's a little bit of delay and we take that point, just like in our lab 1, it has to decide, is that a 1 or a 0? Because it's not all the way up or all the way down. But because it takes a while to make that transition, it's always going to take the 1 or whatever it was before, right? Because it hasn't had an opportunity to change yet. So you can draw them as ideal devices because if I haven't given you clock to queue delay or setup time, whatever they are, but it helps students generally to give it a little bit of a delay. So there's a little bit of unknown here, and then it becomes a 1. A little bit of delay becomes 0, a little bit of delay still 0, little delay becomes 1. Right? And now I can just draw not J, because that's what it is, right? Because if this node is J and that's K, K is by definition not J. With the same delay, right? It's going through the same flip-flop. And then finally, we just go ahead and say Q. What's Q? Well, do you remember the JK flip-flop truth table? Right, if 0, 0, we say the same, 1, 1, we toggle, and then 0, 1 or 1, 0, 1 is reset, 1, 0 is set. So because J and K can never be the same, right, because they're Q and Q bar, the opposite of each other by definition, we're only ever setting or resetting. So then Q, well, Q doesn't know what it is at the beginning. It still doesn't know what it is, right? Because this rising edge of the clock happens, and it's updating based on J and K, which are unknown. So it still doesn't know. But now on this rising edge of the clock, it does have a J and K value. In fact, J is 1, which is set. At this rising edge of the clock, K is 1. And then at the next rising edge of the clock, K is still 1. And K being 1 means reset. And then if there was one more clock, then we'd have a J of 1, which is set. Right, so in this case, Q, the final output, is D, just shifted by 1. Right. Expect some sort of question like this with at least 2 connected flip-flops, right? That you're gonna have to do the timing diagram with clock delays. May or may not have clock to Q as well, but you'll at least need to offset it by 1 clock phase. Yeah.
I have a question. So why is it don't know on the first clock?
Because the J is the output of that. Let me make sure I did this right. Okay, so at this rising edge, first rising edge, D is defined, right? So on that clock edge, J can update. The output, J, can update. But at that same clock edge, it's clocking in J and K's don't know. So the output after this clock is still don't know, because what is the J and K? And then finally that is propagated through and gotten somewhere.
Thank you.
Yeah. Okay. Another type of flip-flop question that I could ask. A little more brute force. Did you take good notes, I guess, question. I can draw something up like this. Oh, forgot one thing. Draw this up and ask, what is this device? Or another way I could ask it is, draw me the schematic symbol for this device as a whole. Right, and these devices, when I ask them, they're going to be devices you've seen before. They're going to be things we've talked about. I'm not going to make up something new for you to puzzle out. I'm going to try and have you identify something we've dealt with, right? Does anyone recognize what this is?
Is it a D latch?
Yes, yes, this is a D latch. So if I asked you what it was, you would write D latch. If I asked you to draw the schematic symbol, you could just do this. Now, there is one, this I1. Does anyone recognize what this I1 is doing? It's an enable. That's all, right? If it's on, these two NAND gates can work. If it's not on, I0 is just ignored, the D input. So, enable, as an enable input. It's a D latch with an enable. It is not correct to have a clock, right? There's no clock signal in this. What is the difference between a latch and a flip-flop?
The clock.
The clock, yes, exactly. The difference between a latch and a flip-flop is a clock. So it could be things like, right, once I have these, I may end up showing you guys what is this device, and I would draw two D latches connected together, right? And that's how we build the flip-flop, right? Is it takes two D latches. And I could do it even at this gate level and connect two of these together to make a D flip-flop and ask you that kind of device. It's just being able to recognize kind of how these building blocks built up from that lecture, right? That I went through and built from an SR latch at a gate level all the way up to a D flip-flop. Pretty limited on what I can ask about there, right? D flip-flops, JK flip-flops, SR flip-flops, and T flip-flops. That's about all. Okay. Yeah, that's actually one of my example questions I was going to do, but I'll skip it. The question could be like, using only D latches, make a D flip-flop. Okay, so I'm going to put set up. There's one of these questions has a lot of writing for me to do. So I'm going to set up an easier question for me to write up here and have you guys spend some time on it while I write the next question. So I said there were going to be counter questions. Here is a good example of a counter question that I might ask. So I might say, given this counter, given this counter, design a circuit that counts from 3 to 6. So we're going, so the 0, 1, 2, 3 here, 4, 5, 6. So we want to count this range. see it. Okay, we good or are we still working? Still working? All right. Okay, so I'll just go over this so we don't spend too long. I get other examples. So what the loads do, right? The load enable is saying, I want to load in a value. Now, turns out in this case, the reset's a bit of a red herring, right? It's misleading. We don't need it. So when do we reset? Well, there's two ways I could ask it. I could just ask the way I did, which is simply draw me a circuit that counts from 3 to 6. Or I could say, draw me the minimum circuit that counts 3 to 6, right? And so the minimum circuit is just taking advantage of the fact that we recognize that the first time that we see 1, 1 is when we reset. So if all we do is take C2 and C1, plug that back into this load enable. And then the load, all I have to do is plug in the value that I want to load from. Oops. So L2 is 0. Right, that's all I have to do. If I was trying to count from 0 to something, then I could just plug into the reset or the load and have 0, 0, 0 at the beginning, right? This, if I didn't ask for the minimum circuit, is equally correct. Something like that, right? It's just that in reality, because I should never get to 7, this last digit is really like a don't care. That makes sense to everyone? Is anyone confused on this?
So if you want to go from 0 to 6, you plug it into the reset?
Yeah, plugging into the reset, except for I would need one. So let's rewrite that question and let's say I want to count from 0 to 6. Okay, does this work?
Don't you want it to reset on 7?
Well, I'm saying let's count from 0 to 6. So I never want to see 7.
Oh, okay.
You need to get rid of the load.
Well, I could leave the load as long as if I don't insert it right. The right way to do something like that is just never load. Or type right that or plug in a 0. Well, it's just I have this bubble here for the active low reset, so I need that. But that would count 0 to 6.
Okay. So it reset on 6. Is that correct?
Yeah, so I would probably say if I intended on you having used the reset, I would say something about its reset condition, meaning is it synchronous or asynchronous?
Okay.
So what you're not wrong, right? Because if it's an asynchronous reset, I can absolutely do it on 7. The issue is that there will be a brief moment where we do get to 7.
Oh, okay.
So, but if you're right, if it is an asynchronous reset, you would have to do it on 7, whereas a synchronous reset is on 6.
Okay. Thank you.
Okay, next question. So I love doing this. There will definitely be some question like this on the exam, where I'm going to give you some code and ask you, what is this device? Now, if I had given it proper port names, it would probably be very obvious. But I want you to take a moment to think about what's happening in this device. And again, it's a device you've seen. And this is part of that homework. If you haven't done that homework 9, this might be a little bit more difficult than if you have done homework 9. Any ideas? Nobody?
That's probably wrong.
Go for it.
Is it a D flip-flop AC?
Very close.
Oh,
It is a D device. So it's
D.
output, yes, D latch.
Oh, okay.
So I have an input H. We could call it, sorry, an input L and M, and output H. Call H Q, where Q is getting assigned to L, the input. Anytime either input changes, but there's no clock. There's no rising edge statement in here. That's your right. That's what you're looking for. If you see rising edge, be strongly suspicious that it's probably a flip-flop, right? If you don't see it, it's probably like a latch or a mux or something else. Okay, so then that's all you're gonna do is what happens, and you can draw out, right? You can draw a timing diagram real quick that just says what happens if these things change, recognizing that change on either L or M. Does anyone know what M is? It's an enable signal. Yeah. Okay. So then the other way I like to do these VHDL questions is really just making sure that you've done the labs and that kind of thing, and have troubleshot it, is telling you there are 5 errors in this code, 5 syntax errors. Find them. And generally, I'll tell you that there's 5 and actually put 6. I think there are actually 5 in this one. Like I try and give, I try and put one more in than I ask you to find. Sometimes I forget to do it because I hate getting stuck. You don't see that one thing. But go ahead and take a moment and find what are the errors, the syntax errors in this code. All right, so let's start yelling them out.
You name your architecture blah, and then end behavioral.
Yep. So blah is an acceptable name of the architecture, but I would have to have blah down here, right? The fact that they don't match, which is exactly what it is a problem. What else have we got?
In your if statement, shouldn't it say if M equals something?
Yes, if M equals 1 or 0. If you said either one, right, or even just said, hey, this is a problem, unless I ask you to fix it, right, then because M is a standard logic, which I can't say. If M was a bit type, this is fine, but standard logic doesn't work. What's our next one?
It's MYST, and then you have MIST.
Yes, exactly. They don't match. Simple typo, right? Thinking that. What do we got?
Semicolon after the standard logic page.
Yep. What do we got? So we've got 1, 2, 3, 4. There's 1 left. Ah, there's 2 left. Ah, I did do 6. I'm good. You got one?
You need to put at the entity, you can say end missed, don't you?
Yes. In the back. What do we got?
Oh,
Actually, still 2 more errors. Yeah.
You're missing 1 semicolon, H equals L.
Yes, I got 1 missing semicolon.
that needs to be assigned to, not equal.
There you go. Yeah, so that's the kind of question I will ask. And I would, in this type of thing, say, find me 5 errors and have 1 or 2 extra. This is a perfectly reasonable thing for me to do. Because sometimes you don't see 1, and I try and avoid making you find all 5. Okay, next question. Trying to plug along right here. So this question is going to read, using these D flip-flops, design me an asynchronous clock divider to get a clock 8 times slower than the input clock. This is my clock in. Make me an 8 times slower clock using only the flip-flops. And this is the same kind of question, right? I did this as a T flip-flop example. I could do with a JK. I'll probably stick to D or T's or something, some question like this. Like another good similar question would be like make a 3-bit counter using T flip-flops and logic gates that resets at 5. That's another kind of question.
Would you plug the Q bar back into D into? Is that right?
Okay, so the first one you said Q bar back into D, and what's the next one?
And then sorry, I'm just making sure. Crap. And then does the Q go into clock for asynchronous?
Yes, exactly. That makes it asynchronous.
And then you kind of rinse and repeat.
Exactly. And so what is this, if I call this clock 2,
That's divided by
and what is the speed of clock 2 relative to clock in?
2.5.
Yeah, exactly. So clock 2 is equal to clock I by 2. Right, so divide by 2, repeat, divide by 4, repeat, divide by 8. Right, that's all. We didn't do a lot of homework on it, but it's directly out of your notes, so I wouldn't feel too bad asking that question. And for those who are focusing, I'll say it again. Another good question would be make a 3-bit counter using T flip-flops and logic gates that resets at N or 5 or some value, right? I won't do that example, but I want you to be aware that that would be a good question. This next one, I like this question because, so I kind of started with some of the harder ones and moving into a couple easier ones. So I would say, and would draw this, so this is a shift register question, and I could either draw the shift register symbolically like this. How do I do this? Or I could draw it with the actual logic gates. And then I could ask, what is the value of this shift register after 4 clocks? Well, this one's pretty easy, right? Because it's coming out this way, and it's going to, the 0 is going to pop out and around and appear back in the other one, right? So this is actually, we haven't talked about it specifically. This is called an end around barrel shifter. And so all that we have to do is follow the 0, right? So the 0 would be here, and then it would go around on the first clock. So 1, 2, 3, 4 clocks. So generally I like to have mostly fairly easy questions and then like one hard one. So like depending how hard I make the timing diagram question that we started off with, that might be the hard one. If I wanted to make on the shift register question the hard one, it would basically be a timing diagram problem as well, where I would ask something like, given this, I would probably do 4 bits, 4-bit shift register and draw the circuits out and have like the AND gates and stuff to make it fully synchronous. Then I could say something like, if you have a 50 microsecond clock to Q delay and a clock of 5 kilohertz, what is the value at 1 millisecond? So 1 millisecond after we start, what is the value of the shift register? And then there you just have to recognize that that clock to Q delay can offset things. And it's fairly substantial, actually, because what part of what that's testing is this relationship that F is equal to 1 divided by the time period, right? So I said there's a 50 microsecond clock to Q delay. And I said F is 5 kilohertz, which means the time period on the clock. So rising edge to rising edge at 5 kilohertz is 1 divided by 5K, which is 200 microseconds. So the clock to Q delay is a full 1/4 of that. Which then if I have a 4-bit asynchronous one, right, then it starts to add up. That would be the harder version of that question. It turns out in the shift register, it doesn't actually break anything. It just kind of slows the ripple down. Okay, the addressable memory question. Actually, is there a question? No, this is fine. Okay. So as I said, the addressable memory question is really like MUX or a decoder question, depending on how I draw it. It's going to have either a MUX or a decoder. It really has to. So I'm going to call this our decoder that has an input of an address, ADDR. Make sure I'm in screen. Okay. And then what the decoder does, right, guys, is it takes the address and asserts one line of this decoder, right? That's what a decoder is. Like it's an unmux, it's a demux. And then these lines, in the case of addressable memory, just have an AND gate in one of the cases, the example that I use. And so this is 0, 1, 2, 3, 4. And then this is bit 4_0. This is bit 4_1, right? And another way of representing that is this is bit 0, 0, bit 0, 0, 1, bit 0, 2, etc. Right? So the contents are bit 0, 0, bit 0, 1. That can just be a 1 or a 0, right? It's just a bit. And so if I give the address of 4, then it would take the contents of these AND gates and put them into some form of register here, right? And then I could ask, and let's call that register P for the parallel output, right? I give it one address, I get n bits, however many bits are there. And then I could ask you something like, what is the value, like, if my address is 100, what is P at 3 or something, right? And then be 0, 1, 2, 3. You come over here and figure out, I give you the values of this. And I might draw the memory as just a grid. Something like that, right? And then the question is, what is P at 3 if I give address 100? Well, 100, come down, find it, find the 1, right? And then you come over 1, 0, 1, 2, 3 at P. That's all. That's like the complexity of addressable memory that I expect. It's just understanding the address and the readout. Other question might be just recognizing that I've shown this to you in notes before. I know we didn't ask homework on it. That's why I want it, and just be like, finish the AND gates or something silly. It's just going to make sure that you paid attention, wrote some notes, that kind of thing. Or it's going to test understanding of muxes, right? Because I could also do something like that, and give it some control signal and say, what is the output? Right. That's all. That's all I'm going to ask on the addressable memory front. Other questions that I might have around muxes, right, is I could very likely ask something like, design me a 16-to-1 mux using only 4-to-1 muxes. Right. And that one again, if you forgot, is I just take a 4-to-1, another 4-to-1, and 2 more, and I connect them up to another 4-to-1. And then each of those has to have 2 input control signals. These 2 share, this first column shows 2 of them, the last column has 2 of itself. Right, so the inputs are A, B, C, D, and A and B just.
Those are your selection signals, right?
Yeah. Then you have to make sure your selection signals are the right 2, more or less. And you can always check that by saying, well, if I give it 0, 0, 1, 0, 0, 0, 1, do I get that node, right? So I0, I1. If I give A, B, C, D, depending how you draw the truth table, however it's provided, then I want to make sure I get I1. Well, is that the case? Well, 0, 0 doesn't give me I1, so that doesn't match, right? So that's not the right truth table for this configuration. That's all. Okay, 16-to-1 muxes. Whew, time flies. Okay. Other questions I could ask. Definitely no generate statements and generics, right? Because I could ask you to write me a quick VHDL to do X that is that we're using a generate statement, or you build me an n-bit shift register, right? Which means you need a generic and a generate, right? So be familiar with those 2. I try to encourage you to use those in the labs. I won't ask you to write an assert statement, I don't think, but I could ask you a question that has or something about, is this assert statement done correctly? And I could like declare a constant to check against, right? So I'd write a for loop and say constant m equals 4. Constant m unsigned, right? Make m an unsigned constant, and then have the thing that it's comparing against be a standard logic vector. And then that would be a code error, right? Because I can't compare a standard logic vector to an unsigned, even if they're the same length, because they don't do it. So I have to do it, would have to do a conversion. I won't ask you, I don't think, to write out a conversion because they're annoying anyways, and I hate them. So let's see, I could also provide you code, say, here's some code, this is what it's supposed to do, and then provide you with an error message from the TCL console and ask you what's wrong with the code based on the error message. Just to make, and it'll be something that you've probably seen almost certainly, or should at least be able to understand. For and generate loops, almost certainly. I could very much like the homework 9 ask you to write me common device VHDL. I'm not going to have you write a lot of VHDL because it just takes so much time and it's not the best use of it. We'll see most of that in the labs anyways. When you write VHDL, unless I say otherwise, and I don't expect I will, I'm not planning to right now. I haven't written the exam, so things change, but unless I specify otherwise, doing things like 4 down to 0 is perfectly acceptable. The shorthand that I tend to use, again, if you write process and don't write the begin, I don't care. If you don't include the stuff in the sensitivity list, that's a problem, right? So things that are just syntax, so the begin, semicolons at the ends, that kind of things, if they're forgotten, no issue. If the vector size is not declared or is wrong, that's an issue, right? once we have the exam, you can ask me if you're just like that. But again, the whole point of it is to not slow you down, right? Make sure that you can just get it out as quick as you can. And just focus on getting the concept of the code right. Again, it won't be too much code writing. It gets tedious. It'll probably be limited to a generic, or for loop, one of those, something like that. I could show you like a waveform alongside some VHDL, say this is my VHDL, it's trying to do this. Here's the output of the waveform. What's wrong, right? And that's just using a waveform to verify the code. I don't have an idea on that one yet, so I'm not sure if it'll happen. I like the question, but I'm not ready for it. Oh, this one. So I like to ask questions about the projects and that kind of thing. So I could ask a question directly about the project, or I could provide, say, code that does something similar to the ALU you guys built, and then provide a block diagram and then ask the question, does this code accurately implement this block diagram? And of course it won't, right? And what you'll be doing there is checking to make sure that in the code that it, like the output connections. Let me just squiggle real quick. So, right, you guys have this ALU and you have these blocks. And then you would just want to make sure things like, does this output actually connect to this input, or did I mislabel the signals? Do they have the wrong size of vectors? Maybe there's like feedback around or something if I drew it in the diagram, that kind of thing. Just ask, did my code realize the diagram? Which hopefully should be easy if you've done the project, right? So that was the point of the project, is to understand hierarchical design. We have, I guess, 5 minutes left. Let me double check that I got through everything I intended on. Yep, I did. So do you have any questions?
Will there be like a practicing here for the last test?
I'm gonna try, my issue is I'm behind on the homework, so I'm gonna try and get the homework solutions out. I have so we have homeworks on 6, 7, 8, and 9, I think are the ones that I don't have solutions out for. I've done the first one, I just haven't posted it yet. I'll try and get them all out by Friday so that you guys have at least the weekend and then Monday to study those. If I come up with, if as I write the exam, that I come up with good practice problems, then I'll start sending some of that over, just probably over announcements kind of thing. So keep an eye out, and I'll throw some practice problems if I can think of good ones. A good way of studying is make sure that you just organize your notes and are clear, because as you notice, some of them are just going to come like right out of the notes. I don't intend on throwing any weird curveballs much beyond what we covered here, because I've had this weird balance that I'm trying to strike, because I feel like some of these I haven't given you enough homework on, but at the same time, I feel like some people are doing a lot of homework, so I didn't want to give more homework. But so anyway, I'm trying to make the exam clear of what will be in it so you can practice what's relevant. No surprises in my mind. You're good to go. I have office hours soon, 15 minutes from now as well. I think you guys will be fine.
One quick question before, can you go over like a counter with a load on it, and just like drawing out the DQ flip-flops, just so I can kind of see that?
Yes, that one, let's see, if I don't have those notes, I will almost certainly screw it up. A DQ with a load.
Or just a counter in general.
Yeah, okay. Okay, so the general idea, we'll see if this turned out as a counter or as a shift register. But the idea ends up being the same. So normally, right, if you had your counter set up, which clock dividers and counters are the same thing, right? Because if you're moving at half the speed each time you go, that's really the same as moving a column left in a truth table. So if I had this, if I want to load a value into this flip-flop, well, the clock that I'm interested in, the counter, are those, right? So if I want, oh, not C0, C1. So if I wanted to make C0 a specific value, I wouldn't intrinsically take Q bar as the next D, right? Because what that's doing is saying toggle, right? Is whatever you were, when I get a rising clock, become whatever you weren't. So instead, I'll just use a mux and do that. And this control signal, so that's my load value, and this is load enable. Because what happens if load enable is 1, and I see this clock, then I can take L0 into D, so the rising edge takes L0 and updates Q with the loaded value instead of just toggling.
Okay, and you would do the same thing for every single bit.
Well, let's double check and make sure it works, right? So the possible issue here, this one we have to think about. So we would like this to be L1, but it's an asynchronous value. So it's not necessarily going to react to this clock, right? So it's easy to load this first one. But much harder to load the second counter value is because what would we like to trigger this? Well, it's actually a little bit hard. So a solution off the top of my head, and it's possibly not the best one, but we already have a weird issue with this clock anyways. So I'm just going to go ahead and gate it. So if I have load enable, now I can pass this clock into here and update that. And in fact, this OR gate may be better served as a mux selected by load enable. That's actually probably the better way to do that is because that way now I don't have a gated clock. Right now I'm just taking one clock or the other one. And so that way, if load enable is turned on, I'm no longer dealing with the asynchronous clock, I'm dealing with a synchronous clock. So it becomes a synchronous load, which is actually, that's probably a good solution. Right. But the idea is the same. Find a way to inject your own value instead of what it wants to be. And it's almost always best implemented with some form of mux.
Okay.